video, we're going to look at the composite model, or to be doing some composite modeling of the 3 layers limited to $1 million, limited to $2 million, and 1 million excess 1 million. In fact, they are additive. All 1 million, if you open your workbook, all 2 million. If you subtract all 1 million from all 2 million, you get 1 million excess 1 million. These were studied before in PTF, and you noted probably very high process correlation to residuals. So let's go to find the composite, which actually sits there. Another way of finding it, if you had a much larger database, is you could go to type of TG, you could go to composite, and you'll see 1M, 2M, 1M excess 1M. In fact, while you're at composite, you could also look at this by, sort of drill further down by line of business. And I think if you click on medical malpractice, this in fact is medical malpractice data, you'll also reach the same composite TG, which is 1M, 2M, 1M excess 1M. Let's open it. Let's now go to, let's suppose you haven't designed a composite model yet, although there's one here that I designed earlier. We're going to design it from start. So let's go to the related PTF models. So you click on this button, select good for each, and with the right button of your mouse, open. Actually, alternatively, if you highlight these 3, you can also click on the you can click on MPTF tab, and I think it'll run these 3. Okay, you can now tile vertically, minimize regression tables, and let's look at the residuals versus calendar year, and you'll see that as you switch tabs, if you go now to 1M excess 1M, 2M, they're very highly correlated. If you close the model display, or minimize it, well, it doesn't really matter, and now you go to CO, which are the correlations, you'll see that they're very high. Let's tile vertically. For instance, the correlation between 1M, all 1M, and all 2M is 0.99. I mean, that is very high. That's between 2M and 1M, very high process correlation. You've got to remember that 1M excess 1M has got quite a bit of data in it, and I mean the numbers are quite big, which means that the reserve distribution for 1M excess 1M has, I think it has a mean in excess of 200 million. If you now close the triangle group, the correlation, and go back to the model display and tile vertically again, you'll see that the trend structure for each layer is the same model. That's what we mean by same model. But the 1M excess 1M has got an insignificant trend. Now, when you model this in PTF, and that's the only data you had, you would actually use that trend to forecast the future. In other words, you would have assumed that the trend in the future, the calendar year trend in the future, is a random number from a normal distribution with mean 5.63% and standard deviation 4.11%. And the reason you would have done that is because there's a lot of process variability, so you can't really tell that there isn't a trend. I mean, a trend of 0 would have been, you would have got better statistics, like a better BIC. But now that we've got the other 3 triangles, we might be able to actually get a better estimate, a more credible estimate of that particular trend. But before we do that, let's revise some of these buttons here. Let's go to model templates. And this is the same thing that you have in PTF. If you estimate the SGI, then it estimates the HGI for each triangle. If you go back to model templates and estimate, say, the statistical chain error, then it does the same thing for each triangle. Okay, so that's model templates. What about loading a model? Load a model, you got a choice of loading a composite model, which there is one or two here. The last estimated model is the model that was last estimated, wasn't saved last time I was in this particular composite data set, and because I didn't save it, it was actually saved, the system saved it automatically and called it the last estimated model. Or you can load related models. Okay, so let's load the related models. Good. Load those, which is where we started off before when we entered the MPTF module. Now I might have mentioned already that if you want to test, because these are very highly correlated, if you want to add a parameter between 97 and 98, because these data sets are very highly correlated, then testing the parameter new trend between 97 and 98, you should actually be adding that parameter to every data set. So at the moment, the switch between simultaneous and independent modeling, by default, it's sitting at simultaneous modeling, meaning that if I had a parameter there, 97 and 98, you can see it's been propagated to every data set. And in this particular example, there's only one cluster, so the option simultaneous modeling clusters, remember this is an action, it would actually add it to every data set. And of course, independent modeling, let's remove that. Go to independent modeling, would mean that if you perform that action 97 to 98 at a parameter, it doesn't do it. But given that these are correlated, the best way to test an additional trend or initial level is by propagating it for all the data sets within the same cluster. If you don't do that, you won't do the testing properly because these are very highly correlated. Okay. Well, it's the same thing with assigning 08. If I assign 08 to the calendar year 98, it's not propagated at the moment. If I remove it, and then I go to simultaneous modeling, and I assign 08 to 98, it propagates it. Okay, let's undo it. Now, what about loading models? Let's go back to loading models, and suppose, perhaps a better way to start here, I want you to load the SGI for each triangle. And remember, the correlations are very high. Okay. Now, suppose I load a related model, but only for all 1M. This means that if I load this related model, a PTF model, only for 1M, for the other two data sets, the SGI model will still be the one estimated. So let's do that. Would you like to run an extra 30? Let's suppose we say yes. Yes. Okay. Well, look at the residuals for 1M. Shocking. So we've estimated good for 1M, but because for the other two data sets, we're still estimating the SGI, and the correlations, click on CO, are very high, it's using the other two data sets to estimate the parameters for 1M, right? So you're estimating the parameters for all 1M using the model good for all 1M, but for the other two data sets using the SGI. And because they're very highly correlated, I mean, you're using the additional measurements, but for the other two data sets, you haven't adjusted for the trends. It's only the SGI. The model for all 1M, which would be good if it was independent, is terrible now. If instead now you've, for example, set the correlations to 0, so go to optimization of residual correlations with a downward arrow, instead of opening the dialog box, it's an action, set all correlations to 0. You've done very well now for 1M. So this principle of when you add parameters to one triangle, you need to add it to the other triangles if they're highly correlated, because you're also using the other data set's data to measure the trends in the first triangle. It's a very important principle. If the correlations are 0, there's no need to do it. So that's an illustration of that. Now, setting correlations to 0 is actually an action. At the moment, the correlations have been set to 0, and if you look down, this downward arrow, the part that's ticked is set all correlations to 0. It's an action. If now I actually go back and load related for each triangle, load, the correlations are still set to 0. It's an action. Okay? So once you set that action, it's going to stay that way until you go back and change it. Remember that. Okay. So now let's go back to use estimated correlations. All right. What's this button? Replicate model. Let's go back again and load model related and only loaded for, no, cancel. Go to model templates, load the SGI for each. Okay? Now, go to load model, related, only good for the first triangle, all 1N. And of course the residuals look terrible. But if you now propagate that model, replicate it, or propagate it to the other two data sets, click on that. Everything is hunky-dory again. Okay? So now you've got a pretty good of these buttons. This is parameter model parameters, parameter constraints, the optimization of residual correlations or process correlation, OC. Well, you've only got one cluster now. All very highly correlated. If you remove all insignificant correlation, nothing happens. If you retain all insignificant correlations, nothing happens. If you estimate, well, no changes were applicable. So you can cancel that. Then you've got the OI, that's optimizing only one triangle, one parameter at a time. That's only for the triangle or the data set that's active. This includes optimization between. Okay, so the way the system would typically optimize is, first of all, parameters within a data set and then between data sets. But of course, if you go to the downward arrow, you can have a choice. You can have constraints within and between data sets, which is default, or just constraints within data sets only, and you don't do cross data sets constraints or set parameters to be the same, or constraints between data sets only, or no constraints at all. You've got those options also. Okay. Now, when you have layers that are very highly correlated, or segments that are very highly correlated, and if you now want to optimize, the best way actually to do it is, because for the alpha parameters, you actually got varying parameters model, the way I usually would do it is one of two ways. Why don't we now, for instance, reinstate all alpha parameters. You do that. You reinstate all alpha parameters. In other words, we had a varying parameter model. That's our original model. We've now made sure that for between accident years we've got, non-varying. We've actually added a parameter between 85 and 86, 88 to 89, and so on, a new level parameter. And we've done that for every data set. Okay? And now you click on 00 to optimize. Okay? And this is the model you get. And now you find out that the trend, the calendar year trend using the other two data sets information, 1mx, 1 million excess 1 million is in fact 0. Let's save that as our optimal model. Okay, so anytime you want to optimize, this is something I didn't illustrate before. I guess I didn't illustrate that before because for the other data set that involved the segments, we only had one alpha for all the accident years. So there was no need to reinstate the alpha parameters. But over here, given that our models for each data set is variant parameter, we reinstate. Now, what is this red band along the accident years? The red band actually says that this trend here of 23.43%, say, is the same as in fact, all the three data sets. Okay, 23.43. I guess here it's also 23.43. Okay, 3 different calendar year trends. This is quite interesting. If we expand the model's display, for 1M it's 6.37. For 2M, the trend is actually lower. Well, that's kind of contrary to what you've learned as almost folklore in your Cultural Actuarial Society course. Well, it just turns out that for this particular data set, the higher values do not trend as much, and that's just a property of the data, where in fact the 1 million excess 1 million has a trend of 0. Okay, you've got model save. You can save the composite. You can also save the related models, the one for each triangle. But I guess that one include the correlation structure. If you go to related and save each one as good one, say, for each triangle, each data set, it'll be essentially, it's cancel it's the model for each triangle, but it can't include the correlations. Because of course, as you save it as a composite, it also includes the it will also calculate the correlations. Whereas you save it as a related model, one for each PTF, you'll kind of assume that the correlations are 0. Okay, residual graphs, model display, correlations, typically are process correlation, but if you go with a downward arrow, you can select parameter covariances and correlations. So, for instance, the correlation in the iotas, well, 1M excess 1M at 0, so the correlation is 0. Okay, so parameters are also highly correlated. Let's close that. You also have a logbook. The most meaningful logbook is really the logbook for the aggregate, rather than the logbook for each data set. Okay, let's close the logbook. Let's do the forecasting now, and just do the forecasting for, say, 2M. So let's remove 1M and 1M excess 1M, and save that as 2M only. Okay. And let's now load the model, same model, assuming we've saved it as optimal. If you haven't saved the model as optimal, just go to Model Save and save as optimal. Now let's load the same model in a new window, optimal. Now we do a forecast. We'll remove the 2M and save that as 1M, 1M excess 1M only. And now, with the right button of your mouse on the forecast summary button, so select all, tile vertically. This is real data. Minimize other types. And you'll see the answers are pretty consistent. So we use the same model, a composite model, to generate a forecast for the data set 2M, and then to generate a forecast for the aggregate of 1M, 1M excess 1M, and the answers are pretty much the same. Now let's suppose somebody in the company says what we really need to do is create a triangle limited to $2 million and calculate the reserve distribution limited to 2 million, and the reserve distribution has a coefficient of variation of 12%, and anything in excess of 2 million is reinsured. Somebody else says in the company, well, you know, the coefficient of variation is actually 12%. We're retaining too much risk. Why don't we limit our losses to $1 million? They create a triangle limited to $1 million, and they get a coefficient of variation which is about 13%. It's about the same. There's no change. Now, why is that? A lot of people say that's counterintuitive. Well, actually, I don't think that intuition works here, because what you're really doing, let me find a spare page or something that hasn't got too much text on it. What you're really doing, let me get the highlighter. You know, if you just had a severity distribution and you change the attachment points, the CV might reduce, but that's not what we're doing here. You know, the distribution of individual losses varies by development year, calendar year, and accident year. The severity distribution varies as you go to different cells in the triangle. What are we actually doing here? We're saying if you take a particular cell, you look at all the losses, any loss that, say, exceeds $1 million, it's truncated $1 million, and you do that for every cell. And the severity distributions change across the cells. So intuition doesn't really work here. So what we find, it's quite an interesting result, and that is that by reducing our limit on the individual losses, we're not necessarily reducing the coefficient of variation. If you take the triangle, the forecast summary that has the aggregate of 1 million, 1 million excess 1 million, and now you got a forecast dialog box, and you redo a forecast. Remove the 1 million excess 1 million. Okay, so we're only going to do a forecast for the data set or 1 million. Save that as 1 million only. Okay. So on one side we've done a forecast for 1 million, on the other side limited to 2 million. Now we click on the right button of the PILD, click on all, select both, and do your reserve distribution simulations from the log normals. Then tile vertically, minimize other types. Then scroll to the right to get the risk capital graph. Scroll to the right to get the risk capital graph. Now let's suppose we go to the 95th percentile on each side, and we'll look at the graph risk capital. That's the one on the top right. Risk capital is a percentage of mean by LRB for VaR at 95%. We do the same on the other side. So the risk capital percentage of the mean reserve for all 2M is 21.88%, whereas for 1M it's 22. It's about the same. So there's no reduction in risk capital requirement at this VaR as a percentage of the mean. What if we select 99%? Is there much variation? Yeah, well, the 1 million is slightly a little bit higher. Okay, so this is very important, I think, in terms of, working out or designing an optimal retention program. I think that you'll find out that in some cases by reducing the attachment point. You're not necessarily reducing the risk capital. Of course, if the premium is a fantastic premium, if the reinsurance premium is a really great premium, then you might as well do that. But you know, I've got quite a few examples where the reduction in the retention level doesn't necessarily reduce your risk capital requirement on a percentage scale. Now let's just revise just very quick before we finish at options, modeling preferences options, and the optimization options, and that's the default, and I think that's where you need to leave it. It might be that you know, when you model net of insurance data versus gross data in MPTF, we might show you later why in that particular example, even though the correlations might be high, you should in fact set the correlations to be 0. Okay, thanks.